let's do an example, and this is exercise 34 from the notes. So here is my claim. And when I say claim, I mean it's something that I am about to prove. My claim is that if this set is a subset of M, then A is an element of M. Okay, before embarking on the proof, let's do this. Let's try to first check syntax, verify that it's grammatical, that we understand at least the grammar involved. Then we'll check semantics, see if we can interpret what's being said. Then we'll go and dive into the proof and do some deduction. So I recommend when you're going to prove something, take those initial steps. Check syntax, check semantics, then go and write your proof. Or, try to come up with your proof, maybe on Scratchpaper, then go and write your proof. Okay, so syntax. This is a proposition, right? So here I have a proposition. It's an equality. And these are two terms here. They're variables, so they're terms. So this is a perfectly well-formed proposition. And here I've got a variable. And if I put a variable bar proposition in curly braces, then this overall becomes a term, which is totally grammatical. Nothing wrong with that. And then a term, and then an inclusion symbol, and then another term gives me overall here a proposition, which is exactly the kind of thing that I can put if in front of. If this thing is true, a proposition is something that can be true or false, then this thing is true, and this is indeed a proposition because it's a membership symbol with terms on either side. Okay, so that's it for the syntactic analysis. It's all grammatical. This is a thing that can be true or false, and so is this. And we're saying if this one is true, then that one is true. Now semantics. So now I want to think about what stuff means here. So this one says A is in M. That's easy. A is an element of M. But what's going on here? So let's start by interpreting the left-hand side. This is the set of K such that K equals A. Think, what variables are free and what variables are bound? A is free and K is bound. So whatever this is referring to, we decided it's a term, so it's referring to some object, right? And whatever object it's referring to is going to somehow be related to A. It's going to involve A, but it's not related to K. K is just a dummy variable. So I should be able to describe what this is referring to without mentioning K. But I must mention A. So let's see, the set of K such that K equals A, that's the set of things that are equal to A. The set of things that are equal to A, or for short, given that K equals A is a way of saying K is the same thing as A, then I could describe this as the set of things that are A. The set of things that are A. Then overall here, what is this saying? It's saying the set of things that are A is a subset of M. Right? Subset. Let's expand that in our minds, kind of. No, I'm not going to write it down. It's too much to write, but expanding what that means, this thing is a subset of M means every element of this thing is an element of M. So every element of the set of things that are A is an element of M. So that's what this overall says. So now reading the entire claim, it says, if every element of the set of things that are A is also an element of M, then A is an element of M. And if you are able to follow that sentence, then it should feel right. But that's all just feeling. Now let's see that the definitions and axioms and theorems that we use actually let us prove what we feel is right. So all of that was just not related to the proof. Okay, so let me create kind of a column for goals like I did last time. And this is scratch work that I would not show in my final proof. So my initial goal is to prove this implication, right? If blah, then blah. So let's assume the first blah and then attempt to prove the second one. So assume that this set is a subset of M. And now my goal is to prove that A is in M. Okay, so I need to think through what it is that I have. I have that every element of the set of things that are A is an element of M. How can I use that to prove that A is an element of M? Well, this inclusion is a machine for proving that things are elements of M, right? It gives you the ability to prove that things are elements of M by proving that they are elements of this left-hand thing instead. So that's a way to think about an inclusion. By universal instantiation, by applying the inclusion to a particular case, it gives you a way of proving that something is in M by proving that it's in the left-hand side here. So a good way to reach the goal, A is in M, would be to prove A is in the left side. So I rethink and I try this strategy. If it doesn't work, then maybe I'll cross this off and update and revert back to my original goal. But for now, I want to try this strategy. I'll prove this, then I think it will let me reach this goal. So notice when I'm looking at my stack of goals here, you kind of need to read it backwards, right? This is my current goal, and it's to help me prove what's above it, which is to help me prove what's above that, which is to help me prove what's above that, and so on. Alright, so how can I prove this? Well, I need to break down what this means. What does this mean? Axiom 5 is needed to break that down. So if I use axiom 5, this means that the proposition inside here, k equals A, holds if I were to replace the k, the variable here, by A. So if you're not sure what I'm saying, or if you're not sure why I'm saying that, then you should pause the video and check that axiom 5 gives you an equivalence between this and this. Okay, so that's what this membership means. So this becomes my goal. And let me actually carry out the substitution. If I make that substitution, my goal is A equals A. Ah, but that's an axiom, right? That's axiom 1. Things equal themselves. So now I know exactly the right next step to take. Then, or not then, but since A equals A by axiom 1, we have A is in the set of things that equal A. So to do that, I'm using axiom 5. So you see what I mean by reading this backwards? Okay, now since A is in this set, and every element of this set is an element of M, we have A is in M. And that's it. So that was a universal instantiation there, where I'm applying this inclusion statement to the particular example A. This inclusion statement says everything in here is in there. And I'm saying, so in particular, if A is in here, then A is in there. And in fact, A is in here, so A is in there. And that's it. We reached the goal, so we are done. Now, do you see what I mean by the proof makes you look smarter than you are often? After you write this first step, what's the next step? What's the right thing to do next? It turned out that the correct next step was to point out that A equals A. Now, if I hadn't shown you this list of goals and I just show you this proof, if I just show you the proof by itself and hide the list of goals, this would make me look really smart, right? Like, how did I know that the correct next thing to do was to point out that A equals A. That seems so random, but then you look at the later steps and it works out. It turns out to be helpful. So that was the correct next step. So this is what I meant by hide your scratch work and look smart by taking exactly the right steps. However, don't be confusing. Don't confuse the reader. So you can see here that every step is justified. So while the reader may be confused as to why I'm pointing out here that A equals A, they don't know what I'm intending, they're not confused about its truth. They at least are convinced that it's true, right? It's clearly justified. So they have no reason to doubt any of my steps. They only have a reason to wonder how I thought of it, but that's okay. Okay, so I'm partly showing you this. So this is not like a groundbreaking result. It's not super helpful for anything. We're probably not going to use this result for anything. But I'm showing it to you because I want to show you an example of what's expected when you're writing proofs. Since you're going to be doing this on your homework a lot. That's basically what you're doing for the rest of the quarter. So notice that I have referenced the results that I'm using by number. This is one thing to notice. Another thing to notice, so you should do this. When you reference a result, reference either by title or by number. It's usually shorter to just say the number. Until it becomes extremely commonplace to use that result, then you can stop referencing it. So eventually, maybe after a week, I'm going to stop saying by axiom 5 every time. I'm just going to use it. But early on, when you've just introduced this axiom or just introduced this definition, you should definitely reference it. And if something is not used so commonly that it would be on top of the reader's mind, then you would want to reference it. Be like, oh yeah, remember that obscure theorem 338 from 2 years ago? That theorem. By that theorem, my argument works. You wouldn't want to leave out the reference there. Okay, so reference your arguments when you're using previous axioms and theorems. Also, notice that I am writing complete sentences with correct grammar, so you should do that. And in fact, I'm just going to remind you that the syllabus contains a rubric, which you should probably look at, or you can just pause the video and have a look at it. And this is the rubric that roughly we're using for grading. Some things to pay attention to are this point that I just made about referencing. You should reference the results you use. Of course, some things are obvious. Your proof should have no gaps. Your proof should be valid. But also, your writing should be good quality. Partly that means use correct grammar and punctuation. So you will lose points for grammar or punctuation errors. An English teacher should be pleased with your result, so you should not submit something that would make an English teacher unhappy. This is not something you're probably used to in a math course, but this is how it's going to be for a while, especially if you take more proof-based classes. Proof writing really is a kind of writing. And I didn't say anything about this point, but examples of misuse of symbols might be, let me show you. Okay, so here I've written something similar to the claim that was on the previous board, and I've misused the symbols. I have abused notation in the bad sense of the word. So pause the video and see if you can decide what's wrong. Okay, and I'll tell you the answer now. And this is actually surprisingly common. The implication symbol here, if you write out what this is saying, so the implication symbol means if-then, right? So this says if this set is a subset of M, if, I don't even know how to write it. It just doesn't make sense, right? So actually the way I see this done is people will usually omit the comma, and they will just write this. So this is how I would write it. It says if because this portion says, if this, then that. So the portion that I've underlined in blue is this part that I wrote in blue. And then you're putting an if in front of it. So it looks like it says, if this is true, then that's true. So that would be a misuse of the implication symbol. And a good way to avoid those kinds of issues is to just use the English when you can, and use the symbols when it makes sense to use the symbols.